4.8 practice problems. The particle diagram opposite represents an aqueous solution of a weak monoprotic acid. White circles represent the hydrogen atoms. Which of the following species acts as a Bronsted-Lowry base in its conjugate acid? In that order in the solution. So, monoprotic means that we are only going to be donating one proton. Conjugate acids and bases are only going to have either an addition or a loss of a proton. We are not going to see a change in the base thing that the hydrogen is bonded with. So option choice A and B are going to be eliminated because we are changing what the hydrogen is bonded to. So those are not conjugate acids and bases. So between option choice C and D, I am going from a base to its conjugate acid. So bases are able to accept protons, acids are the ones that donate them, and we need to go in that order. This, I have lost a proton, so this is more the conjugate base to its conjugate acid. This, I have gained a proton, so this is the conjugate acid to the conjugate base. So option choice D is the only one that matches the description. For the dissolution of hydrochloric acid in water represented above, which of the following pairs includes the Bronsted-Lowry bases? So the Bronsted-Lowry bases are the ones that can accept protons. So they are the ones that are going to be able to accept the extra hydrogen. We can see that when we look from the reactant to the product, water was one of those bases. It was able to accept the proton, so I'm going to go ahead, get rid of anything that doesn't include water. And then if we look from the product back to the reactants, we can see that the chlorine is also one that can accept the proton because we can go back to the hydrochloric acid portion. So option choice D is going to be my Bronsted-Lowry bases, the ones that can accept protons. When 0.2 molar ammonium chloride and 0.2 molar sodium hydroxide are mixed, the reaction represented by the equation above occurs and a strong smell of ammonia, NH3, is observed. Based off of this information, which of the following statements is true? So if we are able to get a strong smell of ammonia, that means that this is going to be escaping the reaction, and we are going to have that evolve as a gas. So if that's one of the options, that's a great option. But looking here, it says that ammonium acts as a Bronsted-Lowry base. It already has an extra proton. It's definitely not going to want to accept any more, so that's a bad answer. Ammonium is a stronger acid than water is. So if we are producing the ammonia and that is escaping, then that means that it is not going back and giving the hydrogen is not escaping the water and going back onto ammonium because water is a weaker acid. It's not really an acid at all. Then ammonium is. NH3 is a stronger base than hydroxide is. NH3 is not going to as readily accept the proton as hydroxide does to produce water. Ammonium and chlorine are conjugate acid-base pair. No, conjugate acids and bases are before and then after we have accepted any extra protons, so that's not going to be the case. Option choice B is the only option that we have. Which of the following is the conjugate acid for NH3 negative? So, NH2 negative. So, conjugate acids are going to maintain the majority structure. We have just added an extra proton. So, I'm going to get rid of anything that doesn't have nitrogen present. And then again, we are adding a proton here. So, I should increase my number of protons by 1, and so B is the only option choice where we have only increased our number of protons by 1, and we have also adjusted the charge as necessary for that. The equilibrium represented above, the species that acts as a base include which of the following? So bases are most easily identified as ones that can accept protons and anything that produces hydroxide. We don't have hydroxide present here, so we're looking for something that can accept protons. The HSO4 donates the protons, so that's not going to be my base. So I'm going to eliminate any option choices where option choice 1 is included. Water does accept a proton here, going to hydronium, so that is good. So option choice 2 being included is important. So that eliminates option choice B. Then we're looking at the sulfate. Sulfate does have the capacity to accept the hydrogen, the proton back, and so option choice 2 and 3 is going to be who my bases are, since both of those species can accept protons. The Bronsted-Lowry bases in the reaction represented above are, so again, the bases are going to be those who can accept extra protons. And so the species that accepted protons are ammonia when we go to ammonium, and then the chloride ion going back to the hydrochloric acid accepted a proton. And so we are looking for the option choice where we have that present. So that is going to be option choice B. All the reactions represented above occur in aqueous solutions of oxalic acid. Which of the following represented is a Bronsted-Lowry conjugate acid-base pair? Again, conjugate acids and bases, we need the main portion to stay the same. We are just adding or subtracting a proton. So I'm going to go ahead and get rid of option choice C, since that does not have an acceptance of a proton and instead changes the actual main portion. So looking here, we are looking for what accepted the proton or gave away the proton. We should only be moving one proton at a time. Here we have lost 2 protons, so that's a diprotic acid. That is not the conjugate acid-base pair. We need the acid-base pair to be just one difference of a proton. So same reason for eliminating option choice D here. We have eliminated 2 protons at once, whereas option choice B, we have only eliminated 1 proton, and so those are conjugate acid-base pairs.